usually difficult to gather at the exact time. I guess that everyone who came from far away arrived safely, and we expect some more people. Hopefully there is not too much delay in the Hungarian rail, but yesterday it was. So it's my pleasure to welcome you on the second edition of the Lamelis Lasers in Medicine and Life Sciences. I guess that who is interested in light, especially in the year of the light, which is 2015, should know that light and life cannot be separated. And this is true for a special form of the light, which is created more than 50 years ago, which is called laser, because when it was invented, from the very first time, everyone was told it will solve a lot of problems in medicine and life science. This is completely true, because since then, almost all directions of the medicine, diagnostics and therapies, and also in advanced life sciences, uses high-tech, including lasers. Szeged was pioneering with the laser sciences in Hungary and even in Central Europe, and a lot of efforts has been done to develop new medical instruments, new medical methods. I guess that I am not a real person who could explain how important steps are in front of us, because the huge laser center is under construction and will be open in a couple of years. So 2 years ago we decided to organize annually summer school devoted to lasers in medicine and life sciences. Is that we like to encourage young people to learn more about lasers, to encourage people to make networks in advanced laser sciences. And it was our pleasure last year that very distinguished people accepted our invitation, and also it is our pleasure that this one-week program will be full of interesting lectures and occasions to see lasers in different clinical applications. So I guess that everyone who is involved in life sciences can understand the importance of having new diagnostic methods, having new therapeutical approaches, and in this year we involve dentistry. Dentistry is one of the biggest users of lasers, since painless dental procedures can be achieved by advanced laser technology, and also the biomaterials which are used in dentistry are activated by different types of light sources. So I guess that it's time to start the program, and I'd like to introduce the rector of the university, Professor Gábor Szabó, who is a full member of the Hungarian Academy of Sciences and one of the pioneers of the lasers sciences in Hungary and Szeged. Welcome you and tell something about the big adventure with the new laser center in Szeged.
Thank you very much. Good morning, everyone. I will speak here as the rector of the University of Szeged because it's an accident. I could be expert in medieval stamps if I wanted to be rector at the university. The real reason why I'm here that we are really still working here since almost 40 years in developing lasers, and especially we have started for activities in short pulse, high power lasers in the late 70s. And these were the technologies that finally led to the technical background of Eli. What I would like to show you is a bit kind of starting from history, because if you ask me what the breakthrough could be after completion of Eli outside, of course, absolutely speaking about the Eli here in Szeged and not the other two pillars. If you ask me, then the honest answer could only be I don't know. I know one thing, however, I'm pretty sure that the real breakthrough that we will see in Eli will not be on the field of laser physics. It has to be on some applications. And this is a very long development of laser physics. Professor Bari has mentioned that the lasers were invented actually 55 years ago. And also very early on, it came up that this new light source should be applicable to biomedical problems. Actually, the real story was that there was a light source which appeared, and you have to use to measure the applicability of light sources. One, perhaps the best figure of merit, is specific spectral intensity. For those of you who are not physicists, this actually means the power of the source divided by the divergence of the source and the spectral bandwidth. The reason why we use this, that this actually tells you how much focused power can you get on target in the desired wavelengths. And if you compare the specific spectral intensity of lasers with classical light sources, there was basically, in a year or so, an increase of at least 12 orders of magnitude. In the meantime, it is approaching the 20 orders of magnitude. So this is actually, if anywhere in physics, something increases by 12, 14 orders of magnitude, then something very new should actually emerge. We could be sure that it will emerge sooner or later. This was actually also the story, the development of lasers. In the very early years, there was a light source, and actually our colleagues at that time teased laser physicists that the laser physicists take the approach that here we have a solution, we should find a problem too. But then, after practically 15 or so years, 20 years at most, the landscape changed very drastically. In the late 70s, there was basically no room for lasers to be published, only because you have a new laser. In the early days, it was enough. It is a laser. We have never done a laser. In fact, I think it was 72 when two guys published a short article about the first edible laser, which was actually a fluorescent laser in jail, basically. Actually, it was more than a joke, because the two guys who authored that article was Arthur Shallow and Theodore Hench, his postdoc in California. Both of them received the Nobel in Shallow in 87 or so, and Hench late 90s. But still, that you could actually take a dye that could be used for lasing and put it into some jelly, that was enough to publish it. 10 years later, it was not anymore possible to publish new lasers because we have developed them. The question, the first question of the reviewer is, okay, but what for? why did you develop this laser? And actually this was pretty much the trend after starting with the 80s, and since then this is actually the key of laser physics. Of course, you are developing new lasers if you want to solve new problems, but always the problem is the first, and then laser is a tool that you perhaps have to modify or develop it to achieve the parameters that you need to solve the problem. And I believe that this is what we can expect from Eli Alps, that it has to be a user facility, the best of its kind. It has to actually offer applications. So basically, we can people are speaking about attophysics, which actually means physics done in the attosecond time scale. But I don't think that attophysics exists yet, because these are very interesting, very important experiments, but these are primarily the proof of principle experiments. For instance, if you wanted to make a pump probe experiment with attosecond pulses, you pump your system with attosecond pulse and then investigate it with another delayed attosecond pulse. These experiments are not working yet, because the attopulses normally have something like, the isolated ones at least, something like 10 to the 5, 10 to the 6 photons. So it is very unlikely that you can catch a photon out of two pulses simultaneously. So basically, keep shooting at your target, and every once in a while, you really see two photons coming from the pump and the probe together. Of course, the whole landscape will change if Eli Alps will be completed, because the photon number is expected to increase by at least 6 or 7 orders of magnitude. That is a whole different world. On the other hand, the other feature of Eli Alps, again, serving experimentalists, is that the repetition rate will be at least two orders of magnitude larger than the current ones, and in some actually high frequency area it will be 5 orders of magnitude. So you will have a much better chance for statistics. You can really make experiments, and you can really do attoscience on molecules that are not selected to produce the best experimental possibilities, but that are selected because they are interesting. What can be interesting in these molecules? One of my favorite examples is that if you think about it, it turns out that we should not have intact DNA in your metal, but barely a few molecules, which is definitely not what we see. And the question is why? Since if a molecule absorbs a photon that has a wavelength that is shorter than 350 nanometers, and we have quite a few photons coming from the sun at this wavelength range, then theoretically chemical bond weighting should happen. Because this is enough energy to break the weakest bonds in these complicated molecules. We don't see that. So then there has to be a process that helps the molecule to get rid of the energy. Of course, we could imagine many processes, but there is another very important thing. If you think about it, it turns out that this process has to be done fast, because we have done 10 years ago some quantum control experiments on molecules, and we have measured, and many others have measured, that the time before real dissociation starts is at most 20 femtoseconds. So the process has to be faster than 20 femtoseconds. Otherwise, the energy will reach the part of the molecule which is the there has to be a process which is non-adiabatic. It means you can really get rid of the energy. The whole Oppenheimer approximation is adiabatic. That is the story behind it. So it has to be something what is definitely beyond the usual approach to treat molecules, or Oppenheimer approximation, and it helps the molecules to get rid of the energy in a time scale of 10 or at most 20 seconds. There is such a process which is actually theoretically well described. The molecules that have more than that are more complicated than diatomics, there is so-called conical intersection. The conical intersection refers to the intersection of the energy surfaces of the molecules. So there is a certain point when the electron cannot decide whether it belongs to the excited state or the ground state, and then it releases energy and goes back to the ground state. And this is very fast, but nobody has ever seen a direct experimental evidence how this happens. This could be, for instance, one explanation to the surprising stability of our molecules that are vital importance of encoding the biological information. This could be an experiment that we could do if Eli were already completed. But this is still like in the early years of the lasers, that there were certain proposals what to do with lasers, also in medicine and biology, but these were really kind of almost linear extension of the present-day knowledge. And the real interesting stuff came a few years later in totally unexpected directions. And this is what I expect from Eli. I told you that we had some ideas what we could do there, like, for instance, study the conical intersection, but this is just the extrapolation of present-day knowledge. And the real interesting stuff will definitely appear a few years after that. So I believe that this summer school is a very relevant and timely one, because one has to prepare for that. These laser systems are not so simple that you take your beaker coming from the street, put it in front of the laser, and that's it. This is not the way. So the experiments that can be done with these lasers are much more complicated and sophisticated, and it requires the knowledge of the given field, like, for instance, biophysics. But you cannot do an experiment if you don't have a slightest idea what the lasers are about and how they work. So we have to combine these two things. And laser physics itself is a very good example how a full field of science can actually turn into serving applications, and I believe that this is really also a very unique characteristics of the labs as well. So I don't want to take your time. I have seen that there is 1 hour for the opening ceremony. I started to panic, and I told Professor Bari that what are you expecting from me? And he actually told me that if we spare staff time, it is not a problem. And I also know that the conference is not, what happens is normally the opposite. We are running after time. So let's this be an exceptional start. That we are definitely ahead of time, but still I wish you a successful conference with discussions, and prepare for the future, because in a few years Eli will really offer very unique possibilities, and I'm very pleased when young people are involved, because the new ideas are normally not coming from people like me who have learned too much already and know too much of the details, and therefore we are not brave enough to go into absolutely unexplored directions. So in you we can kind of really find the real application of PI. So once again, nice conference, and better here in Szeged that you can also kind of leave the city with memories that will bring you back here later on. Thank you for your attention.
Thank you, and I guess it will be very informal this week, so therefore please make friends and enjoy your time, and maybe Dr. Bakar will tell about the 2 days program, what's going on today. After it, we have a coffee.
I think we have a coffee break, and after that, the representative will
Starting the coffee break, that's the best time.
Yeah. Thanks.